Priyanka, and today I'm going to talk about our work, SAILFISH, letting smart contract state inconsistency bugs in seconds. Okay. Smart contracts are computer programs that run on top of an Ethereum virtual machine. Many decentralized protocols use this smart contract to process high-value money transactions. As of 2022 April, the total value locked across decentralized protocols is around 75 billion, which is huge. As they have gained so much popularity, the smart contract have also become the target of attackers as well. A vulnerability in a smart contracts can result in a loss of millions of dollars. One such attack happened in 2016, which is known as a notorious DAO Reintrurancy hack that resulted in a loss of 70 million worth of cryptocurrencies. And since then, there has been a flurry of such attacks happening across several decentralized protocols, resulting in around $1 million losses. To prevent or detect such attacks, there has been research in both academia and industry that span across from static analysis to symbolic execution, runtime analysis, verification. Though it's good to see that we have different techniques to thwart such kind of attacks, however, they have certain limitations. For example, the symbolic execution-based techniques are not scalable for large contracts. Static analysis incurs false positives. They are not precise. Also, most of the prior tools relies on some specific bug signatures and misses others. Therefore, in order to fill in the gap, we come up with a technique to detect two of the most complex to detect smart contract bugs, that is known as reintrurancy and transaction order dependence, or TOD. From this point onwards, I'm going to refer transaction order dependence as TOD. So our technique scales well for large contracts and also achieves precision. Specifically, all the prior tools are either precise or scalable, whereas SAILFISH keeps a balance between these two. In SAILFISH, we introduce state inconsistency, which is a more general definition of reintrurancy and TOD. We then reduce state inconsistency into hazardous access, which is nothing but detecting a read-write dependencies of a common storage variable, which is a root cause of SI. With this, SAILFISH can detect reintrurancy and TOD bugs, including the ones missed by the prior tools. Also, SAILFISH combines static analysis and symbolic execution. Not only that, in order to be scalable and instead of doing a whole contract symbolic execution, SAILFISH summarizes the storage variable of the contract using a technique known as value summary analysis and use this as a precondition during the symbolic execution. With that, SAILFISH can scale well and achieve precision. So let's first understand what is state inconsistency in terms of SAILFISH. So let's say we have a smart contract C and it has got n methods. We define a schedule H that contains the ordered external or public function invocations of C. We have schedule H1 and which operates on an initial contract state S0 and the final contract state becomes S1. We have got another schedule H2 and that operates on an initial contract state S0 and the final contract state becomes S2. Please note that both H1 and H2 contain the same function invocations. Now, if H1 is not equals to H2, meaning that even if both H1 and H2 contain the same function invocations, the order of their invocations are different in both these schedules. Also, if the final states are different, that is S1 and not equals to S2, then we say the contract is said to have a state inconsistency bug. In SAILFISH, we deal with two different kinds of state inconsistency bugs. They are reintrurancy and TOD. Here, the TOD is a subset of the generalized TOD where we only care about whether the transaction order dependence influences the ether flow out of a contract. For reintrurancy, we deal with single function and cross-function reintrurancy and some other variants of reintrurancy. They are create-based, delegate-based, tail-read, destructive write, etc. For the sake of this presentation, I'm only going to talk about the simplest case of reintrurancy, which is single function reintrurancy. To know the details about other bugs, please check out our paper. So let's first understand what is a reintrurancy. So for this, I have a simple example, which is a bank contract that has gotten withdrawal functionality through a withdraw function. The state of the bank contract is displayed on the top right, and we have a user contract that wants to withdraw a certain amount from the bank, and the state of the user contract displayed on the top left. So the initial state of the bank is the bank's balance is around 500 ether, and the account balance of the user, which is represented as a balance state variable, is around 100 ether. So the user first invokes the withdraw function with 100 ether, and the bank will then check whether the user has got sufficient balance for the withdrawal. And if that is the case, it will transfer the amount to the user and wait for the transfer call to return. Now in this case, the bank's balance is reduced to 400 ether, and the user contract balance is now increased to 100 ether. After the transfer call returns, the bank will finally update the account balance of the user, which is now 0. So at this moment, if the user wants to withdraw, say, more amount from the bank, it won't, because the bank will check that the account balance of the user is already 0, and therefore it won't be able to withdraw any more amount. So this is an example of non-reintrant execution, and the final contract state is exactly what we expect. The bank contract is vulnerable to a reintrurancy attack. So let's see how. Let's say we have now this attacker instead of a benign user, and after the first transfer call, like the bank's balance is around 400 ether and the user contract balance is around 100 ether. Instead of returning to the bank contract, the attacker now invokes the withdraw function again. The goal of the attacker is to withdraw more than 100 ether from the bank. At this moment, the account balance of the user is still 100. So from the point of view of the bank, it feels that the user has got sufficient balance for the withdrawal, since it is reading a stale value of the account balance of the user. Therefore, the withdrawal will go through, and the bank balance will be reduced to 300, user contract balance will be increased to 200. However, the account balance of the user is still 100. After both the transfer call returns, the bank will finally update the account balance of the user. However, it is too late, and the account balance of the user is already negative. So in this case, as we can see, the attacker finally could drain out more than 100 ethers, though she only had 100 ether as her account balance. So this is an example of reentrant execution, and the final contract state is exactly not what we expect here. So let's try to understand the relation between state inconsistency and reintrurancy. And let's consider the bank example. So we have seen two different kind of executions of the bank. Non-reentrant execution we define as schedule H1, and the reentrant execution we define as schedule H2. Okay, so here, as we can see, H1 is not equals to H2 because the invocations of the withdraw function in both these schedules are different. And the final state of the bank contract, that is in this case the account balance of the user, is also different. And hence, we can conclude that the bank contract has a state inconsistency bug. So with state inconsistency, what we want to convey is that given two schedules that operate on an initial contract state and result in a different contract state, then there should exist two such operations, read or write, and one of them is a write on a common storage variable such that their relative order of their executions differ in these two schedules. So we define such a read-write hazard as hazardous access. Please note that these two operations from this hazardous access should belong to two different execution paths or two function invocations. So let's try to understand this hazardous access with a simple example. For the bank contract example, this is the two invocations of the withdraw function, and this is an external call in case of reintrurancy. So this is an example of the hazardous access pair. These two read and write operations, which are marked in red, are the example of hazardous access pair. So SAILFISH, in order to detect hazardous access pair, does static analysis, which is known as explorer. Given a smart contract, it builds an interprocedural control flow graph. From that, it extracts the data and control flow relations, and then it builds a storage dependency graph that is known as SDG. After that, it extracts the hazardous access pairs. Now, for each such hazardous access pair, it checks whether the true operation belonging to a hazardous access pair is reachable within an SDG. For example, in case of a reintrurancy for reentrant execution, in this case, it checks whether this two hazardous access pair is reachable from the external call. If it is not reachable, it concludes the contract to be benign. That's because if they are not reachable, probably these two operations will not have any impact at the final contract state, since for both reentrant and non-reentrant execution. However, if it is reachable, then there is a possibility that these two operations will be altered during the non-reentrant execution, therefore can have some impact on the final contract state. However, please note that our SDG is imprecise and path agnostic. Therefore, even if SAILFISH concludes that the two operations within such a problematic hazardous access pair is reachable, it might not be the case in reality. And therefore, it does further verification. To do that, it generates a counterexample, which is nothing but a program slice that contains that problematic hazardous access pair. After that, it employs the second phase, which is known as refiner. So refiner is a combination of value summary analysis and symbolic execution. So during the value summary analysis, SAILFISH summarizes the values of the storage variables and use that as a precondition during the symbolic execution. So let's try to understand what is an output of value summary analysis. So for the previous bank example, we now have three new instructions, which are known as mutexes. So mutexes are a defense mechanism to prevent such reintrurancy attacks. So in this case, if mutex is false, only then one can execute rest of the function and then set mutex true or false accordingly. So for this particular case, our value summary analysis will output that mutex can be only false if and only if mutex is either false or true. So with this value summary and the counter example, SAILFISH does the symbolic execution and it checks whether the problematic hazardous access pair is reachable, and depending on that, if it is reachable, it marks the contract as likely vulnerable. If it is not reachable, then it is benign. This helps the symbolic execution. So these are the two invocations of the withdraw function. So our symbolic executor will execute these two invocations. So after the external call, when it starts executing the second invocation of the withdraw function, at this path constraint, it consults the value summary whether there exists any value of the mutex for the current program state that can satisfy the current path condition. However, mutex with the current program state, our value summary analysis says that, okay, mutex can be false if only if mutex is currently set to false. However, that conflicts with the current program state. Therefore, it is not satisfiable. Hence, SAILFISH concludes that the two operations, read or write, with the, for the hazardous access pair is not reachable in this case. We evaluated SAILFISH on a data set of 90,000 Solidity open source smart contract. We evaluated against 4 state-of-the-art static analysis and symbolic execution based tools. We compare SAILFISH with respect to its vulnerability detection capability and performance. So here are the alerts for all other tools and SAILFISH. So as we can see that SAILFISH around raised 2,000 alerts for reintrurancy and 7,500 alerts for TOD. Though ONT and the Mithril raised like minimal number of alerts, but as we can see that they had issues with both timeouts and error outs for most of the contracts in our dataset. Though Securify and Vandal like emitted more number of alerts than SAILFISH, however, we cannot conclude at this moment whether the emitted alert by SAILFISH is actually good or not. So for that, we manually sample a set of 750 contracts from our full data set and see that there are around 26 reintrurancy bugs in the data set. And then we manually verify all the alerts from the tools. So from that we can see that SAILFISH not only detect all the true bugs, but also it has a false positive rate around 1.5% and 0 false negatives. Whereas the other two tools, that is Securify and Vandal, specifically Vandal has got a false positive rate of 86%, which is huge. So we can conclude that SAILFISH is actually very effective and actually raised minimal number of alerts with respect to state-of-the-art tools. Additionally, SAILFISH found 47 new bugs not found by any other tools. So in terms of performance, SAILFISH is the fastest. It takes around 31 seconds to process a single contract within our dataset. The other two tools, like several other tools, are actually slower than SAILFISH. Specifically, Mithril, which is a symbolic execution-based tool, is 30 times slower than SAILFISH. So to conclude, we presented SAILFISH, a bug-finding tool for reintrurancy and TOD. We generalized reintrurancy and TOD in terms of state inconsistency. SAILFISH combines static analysis and symbolic execution to achieve both performance and precision and scalability, and it outperforms all the state-of-the-art techniques in terms of both performance and bug-finding ability. If you have any more questions, feel free to reach me. Thank you for listening to my presentation.
Thank you very much for this excellent presentation and powerful tool. Any questions from the audience? Yeah.
Hello, thanks for the great talk. So some reintrurancy attacks involve applications that are composed of multiple contracts, like the Uniswap attack involves exchange contract and many other token contracts. So I wonder how SAILFISH could handle such multi-contract reintrurancy issues, and is there any scalability problem with a larger code in such case?
Thanks. That's a very good question. So in our paper, we also discussed about that. And at this moment, there are certain limitations for multi-contract analysis. For example, like in case of multi-contract calls, we need to first detect whether there is an address, static address that is already present in the contract. In that case, we can technically leave the contract to during our analysis if the contract is already present in our dataset and the source code is available. Because SAILFISH right now in its current prototype only works on a source code. So if that's the case, we can lift, and accordingly we can analyze both the contracts like in composition, and yes, we can do that. However, as you say about the scalability issues, as we evaluated around 90,000 contracts, according to our observation, it does really scale well. But yeah, so in that case, if I extrapolate that, I can say it should scale well. Yeah.
Thank you very much.
Yeah. Thank you.
Thank you very much. Any other questions? Okay, we're waiting a bit. I have one question. Okay. So you had this beautiful slide at the beginning, like this fundamental trade-off between precision and scalability, right? So and the current tool still takes more than a block interval in terms of evaluation. Is it possible to make it even faster, maybe less precise, but faster, such that it could be executed in real time when new blocks arrive or new transactions arrive, like on the peer-to-peer layer?
That's a very good question. I haven't really thought about it, but probably, okay, so during symbolic execution, we did some trade-offs between precision scalability. For example, with our current prototype, like the VSA one, which actually helps us to scale well. So in that case, we considered some loops and all to be over-approximate. Maybe if we consider for other more instructions to over-approximate, then in that case, we'll be faster more, and probably, we can technically be much faster than the current prototype. Yeah.
Right, and once you're much faster, then you can even use this as a
yes.
intrusion prevention system or something.
Yeah,
right,
yeah,
right.
Yeah.
Very good. Awesome. Next question from the audience.
Okay. So I'm Zhuo from Purdue University, and it's a very good work. So actually, I have two questions, but the first question is also be answered, like if the attack involves multiple contracts.
Yes.
So I have another question about whether your technique can detect the attack like sandwich attack or price oracle manipulations, because they are also very popular nowadays.
So for the first one, I couldn't probably hear.
Okay, so I mean some attack like the price oracle manipulations, like we change the oracle, the price of the oracle temporarily, and make the lending contract overestimate the value or underestimate. Okay. So can you technically handle such kind of attacks?
Okay. Right now, it only is targeted for reintrurancy and transaction order dependence. So basically, no. With this current prototype, we cannot detect such attacks. Yeah.
Oh, okay. Thanks.
Excellent. We
Thank
have
you.
no more time for more questions, but thank you very much, Priyanka.